So I guess I'm afraid we need to start. So today I will try to cover both perturbation theories, time independent and time dependent one, but probably there will be something still left for the next lecture. I'll see. And one announcement is that you already know your topics, and I don't know who is going to go first. We already spoke about pairing you up, like electronic structure and more topics on dynamics, right? So those will be 2 lectures. It would be also nice before your lecture a week in advance, give me some kind of plan or written notes, maybe so that I can take a look and suggest something to, well, maybe cover or maybe not to cover, that sort of stuff. So please do that, okay? So since you, how many weeks do I have? Next lecture will be the last one of my cycle, and then, yeah, I guess people who will go first try to prepare something for me next Wednesday. Okay?
So one of the problems is that these components are moving, so it's better for them to go together on the last day.
Okay.
To go together on the first day, even though we're splitting our topics.
Mm-hmm.
Would that be okay?
Sure. It will. No, I guess the only little caveat with this is like the person who continues the same topic, he would need to refresh our memory what was said already, so it will not be as efficient. So you plan for that, right? So if you go back to back, then and if you can use a lot of notation and introduction section of the person who was before you, but now in this split you will not be able to use that. There will be no constructive interference in a sense, right? Hopefully it won't be destructive. Okay.
I have a question. How many assignments are we going to be getting in total?
Probably one more for the perturbation theory section. Yeah.
Okay. Can we have that?
You want more or end of the? Sure. Yeah. My only concern is that you won't feel that, yeah, I'm not giving enough.
I feel like I spent, quite a few hours on something.
Good. Right. So it's just there are several concepts we covered, and it's nice to have, as you probably already felt, that it's one thing to listen to me, and another thing is to work out the details, right? So, yeah. So, and you hopefully you understand through that second process more, right, than just listening, and yeah, that's the whole point. So, nothing should be left just uncovered in the homeworks. Of course, there will be some stuff, but hopefully we will be able to cover all the significant parts. Okay? All right, so let me start with the perturbation theory. This is a very important subject, I would say, because of many reasons. One fundamental reason why I like perturbation theory and why I think it's very important to know it is that most of the problems, both in time-independent Schrödinger equation and time-dependent Schrödinger equation, they are not exactly solvable, right? So, independent Schrödinger equation. And so, the way people think about these problems that are new to them, and they potentially, any new problem potentially is not solvable, and it's even more so in the current time because quantum mechanics been for quite some time, and if you face a problem that hasn't been kind of solved before, then it's probably there is a reason for that in algebra, and it's not solvable. But the way to think about these new problems is usually through models or through problems where you know the exact solution, okay? And so that's what exactly perturbation theory does. The perturbation theory for time-independent Schrödinger equation, it tries to build the solution for actual problem from the solution for a problem where we know the answer. Okay, so this ice here. So the example would be, probably you already fed up with that example, but it's very simple. It's particle in the box is an example of solution that has a answer, right? And if you do something with the bottom of that well, right, so then you can easily build the problem where you don't have an exact solution, right? So then H0 would be something corresponding to a system where you have a particle in the box, and H would be H0 plus the potential of X that has kind of corrugated structure or simply just the linear, right, potential in X coordinate. And presumably it has some constant in front of it that makes the whole term small, okay? And so that's the main idea here, is that you wanted to get to the unknown problem from known problem in some kind of way. So, and the analogy in math would be if you don't know how f of x look like, but you know what f of x at some point 0 is, so then you can, the simplest possible way is just to represent f of x as a Taylor series, right? Plus so on and so forth. So these few terms, they kind of give you a sense where the function is going, right? If you know the first derivative, second derivative, and if you know the function at x0, if you don't go too far from x0, so then you can plot the function and or at least know where things are moving, okay? So the key word here is that it shouldn't be very far, otherwise you will need many more terms, right? Now here, when it comes to time-independent Schrodinger equation, the unknowns are energies and wave functions, right? And so you are changing the Hamiltonian, and what you want to know is how that small change will affect your functions and energies, right? So you would start with this, functions and energies, and you want to connect them with the functions and energies of the original problem, okay? And you want to connect them in a kind of Taylor series fashion. The only question then is, what will be analogs of these derivatives in this problem? And we'll cover this today. And similarly, in time-dependent Schrodinger equation, you assume that you know some H0 that can be time-independent, and then you have a potential that is time-dependent. And that makes this whole problem quite difficult to solve. For the reason is that your Hamiltonian is time-dependent, so it's not anymore appropriate to, say, solve the time-independent problem, because your Hamiltonian is time-dependent, right? And then build the dynamics of the time-dependent Schrodinger equation through, just as a linear combination of eigenstates times some phase factors, right? That's what we would do if the Hamiltonian is static. All right, so if we have this, then it's problematic because we cannot diagonalize this. We can, but our eigenstates will be changing with time. They are not going to be as useful as in the case where we don't have V that depends on T. So the solution that time-dependent perturbation theory proposes is that H0 is time-independent. Let's solve first for that guy, or we will assume that we know the solution for this. And if H0 would not like to cooperate, potentially you can treat this H0 as H in the time-independent Schrödinger problem. Okay, so in time-dependent Schrödinger problem, perturbation theory, we would assume that we know this. And then what we will do, we will construct phi of xt as almost like a series, Taylor series with terms like that. So time-dependent perturbation theory, TD perturbation theory, will give us these functions. Okay, and yeah, zero order will be very straightforward, because zero order is like we don't have a perturbation at all, and the zero order will be like a solution for the psi 0 no ice xt equals to I v psi. Right, so, and we know how to solve this problem if we have eigenstates of the time-independent Schrödinger Hamiltonian, right? Then this the solution for this problem is if we know psi x0 linear combination of phi n's, then at later time psi 0 xt is just Cn phi n's minus E ant divided by h bar, right? So that part is easy. Now let me systematically, like this is just an overview, right? What time-dependent perturbation will do for us. It will construct the orders of the function to complete the description of the full problem, right? If we know the solution of the H0 problem. Time-independent Schrödinger equation does the same thing, but for time-independent Schrödinger equation. Okay? And they both kind of look like Taylor series expansion of the solution for these problems. Okay? That's the motivation. Now, the technicality is that what helps. Let's start with simpler time-independent perturbation theory now. Right, and then it's useful to write down. Oh, we already wrote the Hamiltonian, right, in the form where we have this lambda parameter in front of our perturbation, right? And this function of ours that is a solution, it will also depend on lambda, x and lambda, right? Say, and then we have our energy that depends on lambda, and function again. Okay? Now we assume that everything is analytic and we can expand any quantity in Taylor series. So our phi Taylor series with respect to lambda. So phi I x lambda is zero order term plus lambda first order term, and so on and so forth. And the energies, they're also susceptible to expansion, or we also assume that they're behaving nicely with lambda. Most of the physical problems, as I said before, we assume that things are smooth, and if they're not smooth, then we worry about things. But yeah, before we find out that they are not, like things are going the wrong way, then we do not worry much about these complications related to the mathematical structures, right? So it's a physical level of rigor, right? So we have this plus lambda, so on and so forth. Okay. That setup is very simple. Now, what we can do is we can plug these expansions, both of them, in our original expression, right? And then all right, so then this here, will you be able to see here? Okay, so it will be h0 plus lambda v, and then psi I. Okay. All right, so this equation, what it tells us is that we have a function on the left and a function on the right, right? That's a typical setup for eigenvalue problem. Hamiltonian acts on the function and gives you constant times function. But now, those two functions are functions of lambda, really, right? Because they have a lambda dependence. And we assume that they are analytical. So that means, well, and they are equal. So for analytical functions which are equal, all the derivatives must be equal. Okay? What does that mean? It means that all orders of lambda, corresponding orders of lambda, say 0 order of lambda in the left-hand side must be equal to the 0 order in lambda in the right-hand side. First order in lambda in the left-hand side should be equal to the first order in the right-hand side, and so on and so forth. That just follows from the fact that this is an analytical function, that an analytical function, and their Taylor series must match if the functions are the same. Okay? Again, it's not true for any arbitrary function. You can come up with weird functions where this doesn't happen, but here we don't consider those. And so what this assumption allows us to write is now so-called perturbation series equation. So the 0 order will correspond to h0. We group all the 0 order terms, and we will get back in the 0 order our equation that we are assuming that we know how to solve, right? 0 order doesn't require any extra effort, so it's just there, we know how to solve it. And then the first order will be h0 psi I1 plus, I'm skipping kind of lambda here because lambda is in front of every term, and that's why in the left and the right, so you can cancel it. And then you have v acting on psi at 0, and this is equal to, 1 psi 0 plus okay, and so on and so forth. You can write others, second, third equations, right? Mm-hmm.
I don't really think I understood how you got that to like drop the higher terms. Maybe I'm not getting what you did. Like, how did you go from there to there?
From there
Well, we just said
to there?
just look at the zero things, and that gives us an equation. They said now let's look at the
So
zero
like,
and
how can you do that? Is what I'm saying.
Okay, so what I did there, imagine you have a function f, which is x and lambda, function of two variables, right? And what this Schrödinger equation tells me that this function is equal to another function which is also x and lambda. So G is this energies multiplied by function. F is Hamiltonian acting on psi, right? So these are presumably two different functions. I assume they're analytical and they are equal. So that means if I do Taylor series expansion of this in lambda, right? Phi x at lambda, any lambda, I can say 0 lambda, right? Plus f derivative respect to lambda x 0 lambda plus and so on and so forth. And then I do exactly the same for G x 0 plus lambda G prime lambda so on and so forth, right? So I will get two expansions, right? And for analytical function, that means all derivatives must be also the same. So I will equal these terms, I'll equal those terms, and higher terms as well, right? So I will get, for every order of lambda, I'll get an equation. And 0 order is this equation, and this is the first order, second, and so on, right?
How come your superscript, your alias for the first or zero first order changes on the first order equation? So you're going from h naught of psi I1 plus b psi 1 I0. Shouldn't all of them be 1?
No, because V adds, since you see the V contained lambda in front. Okay, so that's why it always, when we have V, it is equivalent to having extra order in lambda, right? So then you can have order less, one order less the function, and then here it's also the same, that E will contain lambda in front of it, which we cancel, and here it's a psi that contain lambda in front of it. Okay? Right, so, and in general, I can probably try to write the nth order, which will be h0 psi I n plus v n minus 1 equals to e n n psi I. No, then it becomes trickier because what we'll get in nth order, not n, say minus k, this is k, this is, okay, let me write down just a sum over k equals 0 to n, and then it will be ei n minus k psi I k. Right? So you have increasingly number of terms in the right-hand side, in higher orders. But the nice thing is, you can see, if, say, we know how to solve this, this equation will contain, this is known term, this is our new function, this is our kind of new eigenvalue, and this is a function again. So we will have something like eigenvalue problems. And at every step, we will be able to find the function and energy of that order. Okay, I'll show you the method that we already encountered, because it involves the projection on the states. These states are complete; they form complete set of states, and that's why we can project these equations on the zero-order states. That's what will allow us to obtain all the functions and all the energies in a kind of closed analytical expression. Okay.
Before the expression is similar to variational.
That's right. Yeah, we will encounter variational problems at some point, but only in the cases where these energies will be close to each other. I mean, the different eigenenergies, they will be close to each other. That's so-called degenerate or quasi-degenerate case. Then we'll obtain some variational problems. But for non-degenerate cases, Actually, it's much simpler. You don't have to solve the variational problem. It will be all analytical. You will see nice expression. That's why I like the perturbation theory. And it allows you, even since everything is so analytical and so simple and straightforward, you will be able to think, at least in terms of like what will be the correction to the energies and to the functions from the first order. So you will be able to understand, you add this perturbation to the problem, where the energies and functions will go. So knowing a little bit of symmetry and the energy scale of the problem, you can actually think about new problems in terms of old problems. That's why it's useful to study models, and then perturbation theory is kind of a glue that, or like, allows you to do a few simple steps to obtain the intuition about the new models. Okay. All right. As I said, we'll use projection technique on this equation, and the simplest one would be, okay, let's just project this first equation. This is the first non-trivial equation. We're projecting it by psi 0 from the left. All right, what we get is h0 psi I1 plus the left-hand side. Right-hand side is this. Okay. Now, the simplification we can easily spot is that Hamiltonian H0 acting on psi I0 will give us EI0 and the psi back, right? So this term will be simply psi I0, psi I1 multiplied by I0, right? This stays the way it is. For short notation, we'll just put it as a subscript II. So whenever I do not specify function, you can assume that they are of zero order, because that's our basis in this problem. And this is equal to this piece. Now you can see that these two are exactly the same, so you can cancel them. All right. And what you're left, and this is presumably you're working with normalized functions, so this is 1, right? So then you got exactly the expression for first order energy correction right away, and it's VII, which is you take the zero order function, you take the perturbation, and you take the integral, right? So that's your correction to energy. Very simple. And yeah.
If the potential energy there, like that correction,
yeah.
If that's just a function, like our operator is just multiplication, can't we pull it out of that inner product, and then the inner product just becomes 1?
No, because it's, as you said, it's a function, right? So, and these guys are functions as well, right? So,
okay.
So you cannot do that. Well,
no, I get it.
you kind of estimate that crude way if v is some kind of function in the range where psi's are large, say psi's are large only in this range, and your function is roughly 10, then you can take it outside of the integral, right, and get something like 10 multiplied by something, right? But in general, you cannot do that. Yeah. But you can use a lot of like symmetry. Unfortunately, is a subject I couldn't cover. But for simple particle in the box, that's, I guess, why it's one of my favorite examples. Here you can see right away if you are trying to find what's the correction to the ground state energy, because you created this odd potential, odd in terms of that if you shift the coordinate system to the center of the box, this function is odd function, right? And so then that integral will be ground state of the particle in the box, which is sine function, right? It looks like this. It will be even function. So this is even, and this is odd. And you can easily say that, well, if 2 even will give you even, then we multiply by odd. It will be odd, and the odd function will integrate to 0, right? So first order correction for a particle in the box when you create the perturbation that has odd symmetry will just be 0. Okay, so you need to go beyond first order. Or, yeah, so for this problem, it's the case. And it actually doesn't really matter which energy level you consider, ground state or excited state, doesn't really matter, because correction for any energy level is this integral. And if this is odd function, product of two functions which are even, well, these functions can be two odd functions or two even functions, or product will be still even, right? So you have an odd number of odd functions there anyway, and so the integral will always be 0. So you don't, if the perturbation is small, the tilting of the bottom doesn't change the spectrum. Okay, this is already quite insightful, right? Powerful. Now, what about function itself here? We kind of lost it through this projection, and now I will try to recover that by doing different projections. So the idea there is that you can project on the same function you are looking. You see here the index I is kind of special index, because we started looking at EI, energy, or psi I function, right? But there are many more. I is just only one. And then it turns out it's helpful to make a projection onto the different states of the first equation. So what we'll get, say we project it on K, K is not equal to I. Right? So we project on K, and we will get H0, I, here 1, plus K 0, V psi I 0 goes to I1. Well, this product is going to be 0 because K is not equal to I. Alright, so this is Kronecker delta, because our basis is orthonormal. Again, we can say, all right, the H0 acts on psi k, right? And that's the function where we know how H0 would act, right? So there is no simplification if we think about how H0 will act on first order function. We still don't know first order function, right? So then we will get 0, and then K0 psi1 plus V Ki equals to EI0 now. Seems like all right, so what do we want here? So what we want is to know about first order function, and yeah.
So on the right hand side we have the two terms. The first one is the Kronecker delta, so it becomes E sub k. Where did it go, sorry? So
yeah.
The definition
Yeah. To 0. Okay, so now we have only this. And the idea here is very simple, that first order function will be expanded as a linear combination of our zero order functions. Okay. Well, simply because they form complete set, right? So H0 is doing at least this for us, that it provides the functions that are complete. So you can expand any unknown function as a linear combination of old ones, right? And all you need then is to find these coefficients. And these coefficients by definition is K0 psi I 0, no, 1 here. Otherwise they would be all 0 or 1. So this is the definition of the coefficients, right? This is how we find the coefficients in expansion, by taking the inner product basis functions times the function we expanded. Okay? And those are the coefficients exactly what we have here, CKI, this, and then it's also here, and they are the same. So you can easily see that VKI divided by EI 0 minus EK 0, that is CKI. This definition allows us to write that this first order function is a sum over k not equal I VKI Now we know how to correct first order function for the ith eigenstate, right? So you need to see what other levels of zero order Hamiltonian it will interact, or the initial psi I zero function, what levels this function will interact through the potential that we impose as a perturbation, and these interactions will be more important for the levels that are closer in energy to the original one, right? So you would expect then that if you have this H0 distribution I and two Ks, K1 and K2, two levels of H0, then something for H, at the first order at least, this level or this function corresponds to this level K1, 0, right? It will admix to the function I much more significantly than K2 function psi K2, because the energy difference is making this to kind of mix with the I function more than the further in energy level. Okay, and that kind of should be familiar to you if you think about molecular orbitals, right? So if you have two atoms, you bring them together, the perturbation would be perturbation of one, like essentially all the Coulomb interaction of all the particles of one atom with the particles of the other atom, right? So, and then you have one s orbital of hydrogen, one s orbital of hydrogen. They are exactly of the same energy, and so they mix very well. If you take H chlorine, right, then one s of chlorine and one s of hydrogen, why don't they mix, all right? But they stay more or less atomic because the energy difference is very big. The 1s of chlorine is because of the chlorine charge is really far in energy, like down there, and the 1s of hydrogen is here, so they don't hybridize. And the hybridization can be understood like a perturbation process, right? Or variational. You can either you can do both. It's just with variations, if you have many states, then it's difficult to diagonalize matrices in your like on the fly, right? But with perturbation theory, it gives a clear analytical expression which levels will contribute to the final answer if you have perturbation that mix in them, the ones that are closer. Okay, so unless there is a symmetrical constraints like the one that S and P orbitals may not mix because they are different symmetry, then energy, that's what is essentially dictating what states will be mixing. Okay. Presumably you know all the states of zero Hamiltonian because those are the model problems. Okay, now I was expecting a question. Why k is not equal to I? I didn't get it.
Is it boring when k is equal to I?
Well, the problem with logic here is the following. I said that this set is complete, right? The zero order functions, right? Now, it is complete when you have all functions there, right? And for any arbitrary function, you can only write that is equal to this expansion if you use complete set. If k is not equal to I, it's not complete, right? So you cannot represent function as a linear combination of others if the set is not complete, right? But if I say, okay, why don't I put I there in the k, then there will be singularity here, right? So there will be difficulty. Now, in order to save the day, I need to show somehow that Cii should be 0. That would save the day. And there is a way to show this. And the way is the following. We impose the condition that function, function must be normalized. And what this means is, in the context of perturbation theory, function must be normalized at any order. And I will just explain this in a moment. So psi I 0 plus psi I 1 norm squared must be equal to 1 up to first order. Okay. So this O symbol again. So we have 1 plus something of the big O of the V squared or lambda squared, so the second order. So it's okay in this norm to have something of the second order because it goes beyond the first, so we don't care about that. But beyond the before the second order, everything must be equal to 1. And so if we consider this norm, what we will get is psi I. This is pretty much psi I 0 with psi I 0, and we know this is 1. Plus cross terms psi I 0, psi I 1, and this is Cii plus the complex Hermitian conjugate complex conjugate Cii star plus the final term psi I 1, psi I 1. And that's the term we don't care about because it's a second order. You see, for this to be true, we need to have these guys to be 0. That kind of explains why we take them 0. Okay? It's from normalization that condition that must be there up to the order which we consider, and that's the up to the second order.
And they have to be, do these coefficients have to be real?
No, not necessarily.
Well, couldn't we just have like an I in there and then put the constant plus the conjugate would cancel each other out?
If they're pure imaginary?
Yeah, if it was purely imaginary.
Yeah, purely imaginary.
I mean, I can just trust you. That was my.
Let me think about it. That's an interesting point, whether they can be purely imaginary.
I mean, I'm all about the hand waving, so I can just say, it's 0.
Okay. We potentially can always rotate the basis so that the functions are real. Okay. One way to avoid this difficulty. So all the functions, say we rotate basis so the functions are real, and then we can avoid the pure imaginary parts, and then the coefficients, if they are pure real, then the coefficients must be 1. It's somewhat maybe a matter of choice of what basis you're working with for the zero Hamiltonian. All right. So another problem with this expression is that even if k is not equal to I, you don't have usually control of how close k and I are. And if k and I are very close, then these coefficients just blow up, and well, it's just expressions become less accurate, as we'll see. But just to complete, I guess we can proceed with the second order, and I will quickly derive what the second order in energy expression is. So for the second order, we will have, let me just stick to my notes, H0 second order I plus V of psi I1 equals to okay. And as for the first order energy expression, what we need is we project on the same psi I at 0 order, right? And then we get this, which is just EI 0 and then psi I 0. Okay, so we can say plus V. Okay, so the V part will be now psi I 0, V psi I 1. And then the right-hand side will have another term like this, which will cancel right. Then the first order term also will be cancelled conveniently because CIIs are 0. And that's what we are getting here. This is CII, which is 0. And then the third term, we have I2 multiplied by psi I at 0, psi I at 0. Right? This is just 1. Right? So what we have is that second order correction in energy 0 is equal to this. And now we can expand our first order correction in wave function. Right? And write down that EI second order equals 2. And then psi I, it's psi k 0, psi k there's a sum here where k is not equal I. This is the second very useful expression for figuring out where the energy will go once you introduce the perturbation. That's the second order. And that, again, as you can see, since it appeared as a result of substituting the first order wave function by its expression that we obtain, right? The energy denominators are there, and whenever I comes close to k, then this thing blows up, okay? And this is not right, and that just indicates that you need to include the higher orders in order to compensate that blow up. Okay, now a few qualitative points here is that, again, you can see the symmetry importance, because in order to, again, look at what will be the correction to ith energy, is that you need to account for all the levels that are coupled with your perturbation operator and coupled to the level you're considering. Okay? And another thing is that if I is the lowest one, so I is equal to 0, then all k's are more than 0, and presumably this EI will be smaller at 0 than EK at 0. But what we have in numerator is just an absolute value of psi I, psi k, right? Because this is a complex conjugate of that, right? So that means that the denominator for this case will be negative. The numerator will be positive, at any rate. So that means the whole expression will be negative. Okay, so the second order correction will always be driving energy below. And so now we can think about this problem from two perspectives: perturbation theory and variational approach. So if H0 and E0 ground state energy, right, and then there is some perturbation, so then if you put into the H expression this psi I 0 as a trial function, what you get is actually you will get the first order perturbation theory correction. You get 0 from H0 part plus the first order correction from just the V part, okay? And that will be higher, yeah, than the true solution after first order. Say true solution is somewhere here. We're going kind of from above. And then the second correction will be definitely lower than this level, right? But it may even, since it's not a variational method, it even could go lower than the true solution. Okay, but you cannot be sure that whether it's lower or not, but it potentially can be. Okay, so that's where I guess simple consideration stops. Okay, now this is all nice, but this only works if you have situation where I level that you are considering are well separated from the other levels, k levels. Okay, and if the gap becomes smaller and smaller, then the normal perturbation theory cannot be used. It blows up. Okay. Now I will show you after a quick break how can we stay in the perturbation picture and deal with the quasi-degenerate or even exactly degenerate case. That, well, has a spectrum, and let's say there is a cluster of states that are very close to in energy. So we will kind of put them as a, well, I with I was a subscript of psi and k is a subscript of I. Okay, so in this particular case we have two of those functions, I1 and I2. Right? And so essentially this cluster of states is not resolved at the level of H0. They have degenerate or very close energies. And if we treat them separately, right? So say we start to build perturbation theory for I subscript 1, right? Then this function will end up correcting this function, right? And we will get denominators like I1 minus I2, both of zero order. And these guys, according to our construction, they can be infinitesimally close to each other. And that construction will blow up. All right? So I call this cluster of states as an inner space. And the outer space is the space of functions that are separated with a good gap from the inner space, right? So now the problem is how to treat the inner space. Because if you think about perturbation theory construction for any of the functions in outer space, then it's easy. You start correcting any function, and then others are well separated, and you can use non-degenerate. But when you try to build the perturbation theory to the states that have counterparts close in energy at the zero level, then even in the first order wave function, you will get terms like that, and that will ruin your construction, right? Now the question is how to deal with that. And it turns out that, well, you go through the same procedure. These equations are still correct, right? And it's just the projection, and the treatment of the projection needs to be done carefully. Now let's proceed, and we will try to build first order correction to the I1, 0, right? So those are the two basis functions that we obtain by solving this problem. Okay. Obtain that. And first order correction, as usual. Let's say we focus on the function I here. Without further subscript, it's either I1 or I2. Generally, what we want to build is psi I, which will be psi I0 plus psi I1, and so on and so forth. Now you may wonder, why don't I just put the subscript here, psi I1 or psi I2? The situation is that this function may be just a linear combination of these bases, right? Because at the zero order Hamiltonian, it doesn't really matter how do we mix those two to get into our later full function psi I. So presumably this will give rise to some psi I1, and this one, well, this whole subspace essentially will give rise to two functions of the total Hamiltonian. And we do not specify what the linear combination of these two functions contribute to each, because they can be in this psi I, they can be just rotated. So psi I 0 equals to, say, alpha 1 psi I 1 plus beta psi I beta 2 psi I, I'll say beta 1 because we consider the first one, 2, and then psi I, well, some other psi I will be with alpha 2 1 plus beta 2 psi I 2 0. Okay. So at the zero order level, we do not specify what linear combination we take, and that will be clear later. What linear combination should we take? Now, right now we just project this equation on our basis. Our basis is these two functions, right? What we have is psi I k A0 psi I 1 plus so it's some psi I tilde with 0, some different state that appears out of this subspace. Okay, so then we have, after projection, I 0 Okay. So now, again, we are acting with H0 on the bra part, and we're getting out of this EI 0, psi I k 0, psi I 1. Essentially, this cancels that. But what we are left with is psi I k 0 v psi I equals to Okay, so that's our equation. It's similar to the previous case. Now the only difference is that this is not anymore a function. This is a linear combination of our two functions. So this k can go either 1 or 2, and this psi I 0 can be some constant multiplied by I1, constant multiplied by I2. And so if we write down now the psi I, the k 0 v, then we have alpha k prime let me change this notation to alpha 1, alpha 2 corresponding to k. And this will be beta 1, beta 2. So then I can write down this. So we summing over k prime, which is different than k, because k is fixed, and the k prime is essentially these two degenerate states that form the zeroth order. All right, and this sum is equal to constant, which corresponds to correction to first order, right? And then here, what we have is a scalar product or inner product of bases with linear combination of functions within that basis, and so that will just give us k prime. Sorry, just k, because this function is a linear combination of this and its and the orthogonal part. Okay, and then when you do the inner product, you get the coefficient. All right, so now this is true for any k, and this is well, to solve for alpha and e's together, we just got ourselves a eigenvalue problem. So it's kind of a now variational approach where we diagonalize the perturbation matrix in the basis of degenerate states of H0. Okay, so if you have your V matrix k prime, right, you multiply it by alpha k prime, sum of the k prime goes between 1 and 2 equals to E, one particular energy corresponding to I, the first order. This is equal to alpha k. Right? So you build the matrix V11, V12, V21, V22, alpha 1, alpha 2. And then you get alpha 1, alpha 2 here. And so that's how you obtain at the same time both first order correction to energy within that subspace and also the coefficients with your original basis. How to, well, build essentially the zero order wave function that will contribute as a zero order to the true wave function when you start including orders of V. Okay? All right, so this is the easy part, and now after that, the situation may actually become very simple, because these corrections you got here, they can essentially split the degenerate case to non-degenerate case. Okay, so you just obtain this energy splitting. These are your I 0, and these are your I, well, 0 plus 1. Right, so you got the splitting because of the V terms. Okay, and so then essentially you lifted degeneracy, and what you can do is go ahead and build the non-degenerate perturbation theory from that point. Okay. Now the first order correction to your functions, to this one, right? So these are relatively simple, because what you do is, as in a normal perturbation theory, you do the projection, but not on this inner space, but on outer space. So that would correspond to the following equations. The outer space functions that are separated from this cluster of functions we were worried about, right? So I will denote them with a subscript n. And so the same projection in the first order goes like this. This is 0, right? So first order of energy is gone. This, when we apply H0 and psi n0, will give us n. And plus V and I goes to okay. And so similarly to normal perturbation theory, we can write that this coefficient of first order expansion of function I is Vni divided by Vi minus En. Okay. So the situation is that our psi I 0 function was obtained in this expression when we were looking for the first order correction to energy. And so it has this both components I1 and I12. And then when we went and looked for psi I1, this already only involves the states from outer space, the ones that are separated well enough from that cluster we're considering. So in that sense, we just sum these ends, which are not equal to i's, and V and I, I0 and 0, and then we multiply this by psi n 0. Okay. Now the only Yes, difference is that this V and I term comes as a psi n 0, V psi I 0, right? And this is not one function, it's a linear combination that we found in the zero order consideration. Or first order consideration in energy, we obtain the coefficients. So this becomes technically psi n 0 V psi I 1 0 alpha 1 plus psi n 0 V I 2 alpha 2. Right, so finding psi I first order for this outer projection is pretty much the same as working with a regular perturbation theory where there is no degeneracy because it only considers essentially the only terms that are left is the ones that are energetically well separated. Okay. And you can go ahead and calculate second order the same way. Okay? So on and so forth. All right, so why don't we proceed with time-dependent perturbation theory in the left 20 minutes. All right, so time-dependent perturbation theory, as I said, was about solving problems like in spectroscopy. You have H0 plus lambda Vt, and you have xt E d psi xt, right? And then this is defined as psi 0 x t. You can, yeah, since I can put lambda as a subscript. It's pretty much the same as putting as an extra variable. But the idea is exactly the same. You just expand your true wave function as a linear combination with the higher and higher orders of lambdas. Right. Plus so on and so forth. Okay, and then as in the time-independent case, you plug in, there's no energy part here, so you just plug in this expression into the time-dependent Schrödinger equation. And you get the left-hand side, right-hand side, two functions which are of which is supposed to be equal, and they are, you presume, analytical functions. So that's why you can connect different orders from the left and from the right and separate different orders from each other, right? And that's what makes perturbation theory so easy to do. Right, so the zeroth order case will be just grouping the zero order terms, H0 psi 0 xt equals to right. So and then the first one okay. So I would like to emphasize again the fact that zero order is solved by considering that H0 is just a static Hamiltonian, and then you can solve time-independent problem first. Right, and write any of your time dependent problem solutions as like first you need to know initial conditions, right? And those initial conditions they come either in the form of some kind of function of x or linear combination of eigenstates of zero order problem, time independent problem. Right, because it's only, so it's the initial condition, so that means it's at zero time, there's no time dependence yet. And then in order to get time dependence, or in order to solve this equation, all you need to do is to add the zero order eigenstate multiplied by time. Okay, I will remove h bar, but no, technically it should be there, but since we're writing things without h bar here, so I don't put it. We're assuming atomic units where h bar is 1. And so that's our solution for zero order. Okay. There are many ways to solve this kind of zero order problem. This one is the most straightforward, the easiest. The only trouble is that you need to know the solution of H0 equation, right? And that sometimes is difficult and sometimes is unnecessary. Simply you can skip that part, but if you represent your initial condition as some other basis functions, not the basis functions that are eigenstates of H0, then adding the time dynamics will not be just adding the coefficient, will be more complicated ways to do this. Okay, that's why for the sake of just moving on to the perturbation theory, I leave it like this. Presumably this can be solved. And then we'll go to the first order. I'll illustrate how the first order can be tackled. All right, so okay, so what we can do we assume we have these functions, eigenfunctions of H0, then we can write psi n of xt as a linear combination some time functions dn of t multiplied by phi n of x, right? In a sense, time-dependent perturbation theory is easier because you don't have energies here. So all you care is like how do you obtain the functions, and these functions, this f of n, they form complete set. So you can just simply expand the spatial part of any function is a linear combination of them, and then dn's are something that is left, and so you can now formulate the problem of finding this as a problem of defining the dn's. Okay. So the way you do it, you have an equation, and then you just plug this expression into the equation and use the fact that H0, when it meets phi n's, acts in a very simple way, producing energies. Right? So you have H0, dn. dn's are immune to H0 because H0 is time independent, so it acts only on the phi n's. So it will give us, I will just write these three terms, 1, 2, and 3 separately, and then I'll combine everything into the first order expression. So this will be sum over n dnt H0 acting on phi n of x Okay, so then v, with v, okay, we don't do much. We just remember that our function psi 0 xt is now this function. So it is sum over cn's phi n's exponent minus I and t. And v can be potentially x and t operator. So it will modify both, can modify potentially both this exponent and the fn of x. And the third contribution is differentiation. So when we differentiate, we get, in this form, we only differentiate dn's, the phi n's, they are time independent, right? So we get sum over n as a third term. And then, like we usually do, once we have a good complete basis, we just project from the left by all these phi n functions, and we integrate spatial variables. So our equation for the first order becomes, say we multiply and integrate by phi k, right? And then what we have is sum over n dnt en phi n, right? This is the first term plus we have second term writing on the okay, and then this is equal to last term okay, and this part is not space dependent, so we can take it away, and what we get here is sum over n dn dt phi k phi n. This is our delta Kronecker and k, and this becomes I, no sum anymore, d dk over dt. That's our answer for the right hand side. This term is, we cannot neglect v because it's a function of x possibly, right? So we have k v, but also function of t, and t cn sum over n. So that's, well, the only simplification we can make is that we can call this v kn t function. So it's now functional only t operator or t variable because we integrated the x part, spatial part, right? And then this is also simple because these two, they do not interfere with our space integration, and you get again delta Kronecker function. Multiplied by dn en, right? And then this becomes just dk t ek. All right, so the final expression can be written now the right hand side, let's put it the left hand side, and then we have dk function of t e k constant plus, if we look at this expression, this comes as a result of setting up the initial condition, right? And this can be calculated if you have v and phi's, the energies are also coming from the zero order problem. So we can, though it looks complicated, but this whole thing you can just call f that depends on k, right? The n is summed, so it's just the f subscript k of t, and that's the expression, which is nice because we don't have a connection between different dk's, right? So the derivative of dk depends only on dk and some other functions. Okay? Do you know how to solve this equation? What if there were no fk? Just this. Would you be able to solve it? Right? Cool. So then there is a method that is called kind of variation of constant. That's one way to solve this equation with f part. first you solve without f, you get some extra constant from the integration, and then you assume that that constant is actually a function. And you formulate the equation on that function, and it's all very simple. But we could, what we could do, yeah, let's say we solve the expression d over dk dt equals to ek dk, right? So the way we do it, we say, okay, d dk dk equals to ek with minus I dt. You integrate. Here you got logarithm of dk equals to minus I ek t plus constant. And so then dk, the function of t, is c exponent minus e I kt. Now there is this constant, and you say, all right, why don't I make this a function of t? Because I'm not solving this equation, I'm solving that equation. All right? And so if you do that and plug this expression into the original differential equation, then you would need to differentiate a product c over t minus e k t, right? And that would be equal to c over t no h bar. Okay, so this is d, and there is the energy, plus there is this fk function. Okay, so you will see now why this is useful, because when we differentiate, you differentiate c first, then you will also differentiate the exponent, and that's where simplification comes. No t. All right, so there is I minus I, they go to 1, and what you're left with, ct ek exponent, which is exactly the same as here, right? So this part and that part get cancelled, right? And what we have now is very simple left-hand side, which is equal to f of k t. And so then you easily differentiate, integrate the c of t being integral from, say, 0 to some t, here d tau, and then the rest is minus I exponent plus I k tau multiplied by f k of tau. Okay, so that's the solution for C part, and now you can put it in a solution for D part. Right, so combining two together will, well, essentially this C of this is the solution essentially, and then C over T is this. Okay. And you can note that essentially time dependence here and time dependence here, though they have here it's positive I, here is negative I, they don't cancel each other because this is at the final t and these are at intermediate tau. So we're integrating from 0 to tau, from t to t. Okay.
What is the first term after the integral?
D tau. This is the d tau. So you can either put in the first or last, and then there is minus I, constant exponent, and our function f, which will be pretty lengthy to put there. Okay? So I'll explain what this all means in a simple example next lecture. Okay? This is just the basic derivation, time-dependent perturbation theory.